name is Jade Baston and I am a second year civil engineering student at CQU in Mackay. You are about to watch my informative video on structural load types. A structure is a system of connected parts that work together to support various loads. Under applied loads, the structure must not fail, maintaining its original shape and continued stability. When designing a structure, the design engineer must take into account safety, aesthetics, serviceability, economic and environmental constraints. The most common types of structures found around the world are trusses, cables, arches, frames and surface structures. Once a design has been formed, each element needs to be analysed on its own and as part of the entire system to ensure that it has sufficient stiffness and strength to support the loads it will be subjected to. Examples of structures are bridges, towers, ships, aircraft, tanks, and pressure vessels. A load is defined as a force or acceleration that is applied to a structure and its components, which in turn can cause stresses, deformations, and displacements within the structure. These reactions can be in the form of compression, tension, shear, or torsion forces. For the structure to remain stable and safe, it needs to be constantly in equilibrium, where the forces in all directions are equal to zero. Newton's third law is also relevant in the design of structures, where for every action there is an equal and opposite reaction. The structural load types I will discuss in this video are dead load, live load, wind load, snow load, earthquake load, thermal load, and settlement load, with the most commonly used being the first three on this list. Dead load, also known as permanent actions, is the weight of the materials used in the structure and any permanent fixtures such as structural members, columns, beams, girders, flooring, roof cladding, windows, plumbing and electrical fixtures. It does not increase or decrease, shift or move over time. It is usually calculated by using the density of the materials and dimensions of the design. A general rule of thumb is that the larger the structure is, the more accuracy that is needed in the dead load weights. For example, a two-storey residential building versus a high-rise residential building. From Australian Standard 1170.1, I have selected a few common material densities for this table. As you can see, their unit weights vary quite a lot, so material selection is an integral part of the design process to ensure that the structure will not fail. Live load or imposed actions are loads that are caused by the use of the structure and are of varying magnitudes and position. These such actions can include, but are not limited to, temporarily placed objects like furniture, moving vehicles, and pedestrian or occupant traffic. In some countries, other environmental factors like wind and snow loads are also included in the live load calculations, but in Australian standards are defined separately. This table contains some of the minimum live load limits contained in Australian Standard 1170.1. It can be considered common sense that the potential for more occupants in a building will in turn call for higher minimum imposed loads. Wind load is the pressure and suction forces on a building that are caused by the flow of wind through and across the structure. It is primarily a horizontal load with the movement of air being relative to Earth. Wind loadings are dependent of geographical location and its historical records, height and shape of the structure and surrounding environment, including nearby obstructions and earth contours. Wind loads have the potential to cause tall structures to sway. In these cases, cross-bracing is used for extra stability. Cladding must also be secured to the structure, along with the dead load being heavy enough to hold the extra weight of the cladding and resist wind loads imposed on the structure. Snow loading is caused by the extra weight from snowfall. The calculations of snow loads are dependent on the roof geometry, building insulation, wind frequency, duration of snowfall, geographical location and historical depths. In general, the steeper the pitch of the roof, the less the snow load limit will be, as snow can slide off more easily than if the roof was flat. Australian Standard AS 1170.3 expresses that the only areas that snow and ice loading is applicable to is parts of New South Wales, Victoria and Tasmania. Earthquake loadings are caused by the ground's motion during an earthquake, which causes distortions within the structure. Earthquake loads are dependent of seismic activity of the proposed site, and the risk of earthquakes are relatively low in Australia, as the entire country sits in the centre of a tectonic plate. Other countries, such as New Zealand, Japan, and the western coast of America, are situated right on the edges of tectonic plates and are at a high risk of earthquake occurrences. All materials expand or contract to differing degrees with temperature change and hence are susceptible to thermal loadings. Material selection should be tailored to the environmental conditions of where the structure will be erected. Expansion joints are most commonly used to allow for the expansion and contraction of materials without causing damage to the structure. Settlement load occurs when the soil settles under the weight of the structure. This can happen quickly or over a longer period of time and is usually uneven, which causes movement and stresses within the structure. The Leaning Tower of Pisa is a very well-known example of this settlement. The Australian standard that is used to calculate structural loads is AS 1170, Structural Design Actions, and is broken up into the following substandards. 1. Permanent imposed and other actions. 2. Wind actions. 3. Snow and ice actions. And 4. Earthquake actions in Australia. Structural failures due to insufficient load calculations. The Tacoma Narrows Bridge failed and collapsed in 1940 after it twisted and vibrated due to unexpected wind loadings. The Hyatt Regency Skywalk collapsed in 1981 because the structure could barely hold a dead load, let alone any live loadings. The Metrodome in Minneapolis collapsed in 2004 due to a combined snow and wind loading. Thanks for watching my video. I look forward to receiving your feedback.